In Lesson 8.8, Power Series, we will continue our exploration of Taylor approximations, and in this lesson, we're going to find out where that Taylor approximation actually becomes a good approximation for the function it is approximating. What I mean by all this is that we may end up with a function of some sort, and let me just draw a random function here. Don't include this in your notes. This is just an example. But if I have a function that looks like this, for example, and I create a Taylor approximation, in fact, this would probably be a Maclaurin approximation since it is centered at 0. But what we're going to do is find out in what neighborhood our approximation is a good approximation for the given function. We call this neighborhood the interval of convergence. It's always centered at C. That is the same C that we use to build our Taylor series around. And that interval will extend out a distance that we call the radius of convergence. So as you see, if we put our center together with our radius, that is how we're going to form what we call the interval of convergence of a power series. Now, I did say that this is used for Taylor approximations, but a power series itself is simply a series in which each following term is x minus c raised to the next power. So you can see this is a polynomial type series. But of course, we'll go a little bit more in depth than that. Anyway, all this being said, why don't we begin by looking at a few rules towards finding the radius of convergence. We'll do a few examples where we find the center and radius, and then we'll put it all together to find that interval of convergence. So let us begin this lesson by actually finding out how to determine the radius of convergence, which we'll call R, for a given power series. Now, in a power series, we're not going to refer to each term as A sub n, simply because each term will in fact have an x in it. So we're going to call them U sub n. And in order to find the radius of convergence, actually all we're going to do is something that we're already very familiar with. We're simply going to do the ratio test. And how we're going to do that is just like before. We're going to find the next term. We're going to divide it by the current term. And because we do want these to converge, we're going to set this to less than 1. Again, all this is just the old tried and true ratio test. So nothing new here. Now, the ratio test could result in 3 different conclusions here. The first conclusion is that we can get something nice like x is less than 4. Well, if we get something like x is less than 4, then our radius of convergence is 4. Easy enough. However, what if we get something wacky? Let's say we do the ratio test and we find out that the limit of the ratio is actually 0. Actually 0. If we find that out, then what we can conclude is that the radius of convergence is in fact the entire domain. And I'm going to write this here, but it is the entire domain. Another wacky conclusion that we can reach when we do the limit of the ratio is that it might equal infinity. If it does equal infinity, then the radius of convergence is actually the easiest thing we can possibly think of. It's just 1 point. And when I say that the radius of convergence is just 1 point, it should be fairly obvious exactly where that point is. Remember that our power series, whether it's a Taylor or Maclaurin series, is built around a single value. Essentially, it touches the original function at one value of x that we call c. If the radius of convergence is just 1 point, then that 1 point is c. So, given all this information, let's go ahead and take a look at a couple examples where we'll examine finding the center of convergence as well as the radius of convergence. So, in our first example, we're going to try to find the center of convergence as well as the radius of convergence for this given power series. Now, I'm going to begin by talking about the center of convergence. This is actually really a very, very easy thing. Every power series will have some term in it that says x raised to the nth power. And that particular term is going to just give us the center of convergence. In this particular case, the term says quantity x plus 3 raised to the nth power. And what that's going to tell us is that the center of our interval of convergence is actually going to be at -3. And I'm going to call that center C. And that is the value upon which a Taylor series is built around. At C equals -3, or at x equals -3, we'll find that this particular power series agrees with its function exactly. All right, so that's how we find the center. It's a very, very easy thing. You can do it just by looking. There's not much to it. However, to find the radius of convergence, we are going to have to run this through a ratio series test kind of thing. Remember that when we do the ratio test, we're actually looking at a magnitude of ratios. So what I'm going to do is start by looking at the next term. In this case, that's going to be x plus 3 to the n plus 1th power divided by 2 to the n plus 1th power. So there's our next term. And remember that we're going to divide that by the current term, which, as I said a while ago, I'm going to do by just multiplying by the reciprocal, as that would be my first step anyhow. So there is our ratio test, if you want to consider it that way. And of course, because we're trying to find where it converges, remember that the ratio test does converge for all values less than 1. All right, well, let's do a little bit of simplification here. I'm going to keep my limit statement going. But when I simplify, notice that I'm going to have one more quantity x plus 3 on top than I will on bottom. So here's my quantity x plus 3. And notice that I'm going to have one more 2 on the bottom than I will on the top. So it's going to look like this. Now, there really is no remaining n's for me to deal with. So at this stage, even though it's not really correct, I can kind of get rid of this limit statement. What I'll say officially is that I am doing the limit as n approaches infinity. But because there's no n's, I didn't really have to deal with anything. So in reality, let's face it, I just got rid of it. It's all good. All right, well, take a look at this statement here. This is beginning to look like the end of this problem. What I can do is, because my center is based around -3, I do want to end up with this term by itself. All right, that is the magnitude of the quantity x plus 3 that defines my center. So what happened to the 2 in the numerator? Well, I just multiplied both sides by that and acquired this inequality. Quantity x plus 3 is less than 2. What does this tell me? Well, I already found my center at -3. My center is intact. That's very important. And what I'm going to find is that my radius of convergence in this case is actually 2. And where did I get the radius as 2? Well, I got it from right there. So, in this particular power series, it is centered at -3 and has a radius of 2. I'm assuming that in your head, you're probably thinking where I'm going to go next with this, but I'm going to pause. I'm not going to get there just yet. Let's take a look at one more example, and then we'll explore the interval of convergence. In our second example, we're going to explore finding a center and radius of convergence for this particular power series, but I do promise you one thing. This example is going to be 10 times more fun and 18 times more exciting than the first example. Why is that? Because it's not going to work out quite as nicely as the last one. I'll show you what I mean. The first thing we need to do here is find the center of convergence. And if you notice this time, the x term is not an x plus 3 like before, or an x minus k, or any of that garbage. This is simply x raised to the power of 2n. And what that tells me is that the center of convergence for this power series is going to be c equals 0. So that right there makes this a lot more fun and exciting than the last one, in that we didn't have to figure out really much of anything, to be honest. But if we take a look at the radius of convergence, this is where the good times are to be had. We're going to go ahead and do our limiting process, and let's do the ratio test. If I plug in n plus 1 for each of these n's, notice I'm not going to get 2n plus 1. Rather, what I'm going to get is 2 times the quantity n plus 1. And if I expand that out, this will give me actually 2n plus 2 factorial. Of course, we're going to multiply that by the term x to the 2n plus 2. And we will divide that by, well, here's a regular n plus 1. Nothing special there. So there's our next term. It's a doozy. But if we multiply by the reciprocal of the current term, that'll give us our n factorial on top, quantity 2n factorial, and then x to the 2n power in the denominator. And of course, just as before, I want this to be less than 1 so that it converges by the ratio test. All right, well, again, just like with our first example, we need to go ahead and clean this up a little bit. So how are we going to clean this up? Let's start with this 2n plus 2 factorial that we have right here. This, of course, is going to somehow interact with this 2n factorial. And how are we going to deal with this? What I want you to do is consider writing out the first few terms of this factorial. Of course, we'll have 2n plus 2. That'll follow with 2n plus 1, and then 2n, and then all the way down. Well, that 2n and the 2n in the denominator are going to cancel out. And so what I'm going to be left with here is just the 2n plus 2 and the 2n plus 1. All the other terms will cancel. Similarly, if I have x to the 2n plus 2 on top and x to the 2n on bottom, simple algebra 2 exponent rules will tell us that we will just be left with x squared. So good times there. If we look at the denominator of this, of course we have n plus 1 factorial. If we write that out, that's n plus 1 multiplied by n, multiplied by everything below n, which will actually cancel out with this n factorial on top. So what are we left with here? We are simply left with n plus 1, that is all. All right, again, I'm going to make that less than 1. This time, the n's did not all cancel out. I do need to do the limit as n approaches infinity here. And if I do this, what's going to happen? Well, if you don't see what's going to happen immediately, let me go ahead and take a second and just go ahead and multiply these two binomials together. You should already see what's going to happen, but just for the sake of brevity, if you like, there is the product of those two binomials. I still have x squared in the numerator, and I still have n plus 1 in the denominator. But I'm going to set that to be less than 1. And now let me do the limit as n approaches infinity. There's no hiding it now. The numerator is of a higher degree than the denominator. And as such, all of this stuff right here is really just going to go to one big infinity. So what do I end up with here? I end up with infinity is less than 1. Clearly, that is a flawed statement. Infinity is certainly not less than 1. And so what is our conclusion going to be here? What we're going to conclude is that the radius of convergence is actually just 1 point. Just 1 point. So I could write it that way, or if I want to write it more mathematically, I could say that the radius of convergence is equal to 0. There is no radius of convergence. It only is convergent at that 1 point. And you might ask yourself, at what point is that? Well, it's at the point 0. So at the 1 point, c equals 0, that we built this entire power series around to begin with. All right, I promised you fun. I promised you exciting. And I feel that I did deliver. So let's go ahead and move on to our next set of examples, which will involve intervals of convergence. Of course, that will use the center and the radius to develop this interval. Before we get there, let's take a look at one more box here on the bottom right of your notes, where we will define how to find that interval of convergence. So you may have already made your conjecture about how to find the interval of convergence. It's actually a very easy 3-step process. And 2 of those steps we've already done. The first thing you need to do is find the center of convergence. And again, a lot of times you can do that just by looking at the power series. You can just kind of tell. After we do that, we need to find the radius of convergence. And that we've already explored how to do with 2 examples, just using the ratio test. The center, I'm going to call C. The radius, I'm going to call R. And the last thing we need to do is once we set up our interval, of course, that is the center minus the radius at the beginning and the center plus our radius at the end. What we need to do is check our endpoints. It is possible that our endpoints will either be included or excluded from our interval, depending on whether the endpoints converge or diverge. And we need to check both endpoints every time. So we're going to set it up as C minus R, C plus R. And again, I'm going to do that here, 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 and here. There are a number of ways that our interval might look. So let's see what this looks like here. It's possible that both endpoints converge. And if so, then they are to be included in our interval. And our interval looks like this. Perhaps only our first endpoint converges and our second endpoint diverges. If that, we have a case like this. Or maybe the reverse is true. Maybe our lower endpoint diverges, but our upper endpoint converges. Or, of course, you can probably figure out the last one. Maybe both endpoints diverge. So these are 4 of the 6 ways that our interval of convergence could look. However, I do want you to consider what would happen if our radius of convergence is 0. What would our interval of convergence look like then? Well, it would just be x equals c. Of course, if you plug in 0 for r, we get c comma c, and that's our only point where we will converge. Finally, what if our radius is infinite? Well, if you plug infinity in for any of these for r, what we'll find is that the entire domain is our interval of convergence. And if that's the case, then I'm going to say that x is included in the set of real numbers, or you could write negative infinity to positive infinity. Either way will work. So as you can see, there are only 6 different ways that our interval of convergence could look. It all depends upon our center and our radius, and then we check our endpoints. So let's take a look at 3 examples of this, and I think everything will become clear through the way of example. So as usual, we're going to start with a relatively easy example for finding our interval of convergence. The first thing we need to do is actually take a look at this and see if we can find the center of this power series. And that shouldn't be too difficult. Notice that this is not x plus anything really, so it's just 3x to the n power. And what that tells me is that our center, in this case, our center will be at c equals 0. Not too bad there. Now, to continue with this problem, to find the radius of convergence, just as we've been doing, we're going to do the ratio test. So we'll do the limit as n approaches infinity of the magnitude of this. Now, the next term in this power series will be 3x quantity to the n plus 1 power. And on the denominator, we'll have 2n plus 2 factorial. Remember, even though I'm sticking in n plus 1 for each n, I need to distribute the 2 out. So I do get the 2n plus 2. When I multiply by the reciprocal of the current term, I'll end up with quantity 2n factorial divided by quantity 3x to the n power. And of course, I'm looking for convergence, so I'll set that less than 1. Well, a little cleanup is in order here, of course, and I certainly welcome you to work ahead of me on this. But if I take a look at this, the quantity 3x's, those are essentially going to cancel each other out, and I'm just going to be left with a 3x on top. And as far as this quantity factorial part, well, we took a look at something very similar to this when we did example B. So for the sake of brevity, I'm just going to go ahead and write this 2n plus 2 times the quantity 2n plus 1. Again, I do want that to be less than 1. So now all we need to do is perform our limiting operation. As n approaches infinity, I hope it's clear for you to see that this entire magnitude here is actually just going to turn into a big 0. We end up with n squared on the bottom and no n's on top to balance. So this does go to 0. Setting that less than 1, I see that I have a true statement. 0 is less than 1. Let me follow that up by saying 0 is always less than 1. And so what this tells me is that our radius, since this is always a true statement for all values of x, our radius is going to be infinity. Well, if our radius is infinity, it really is irrelevant where our center is. What I'm going to conclude here is that this power series converges for all values of x that are in the set of real numbers. Or, if you prefer, it converges for negative infinity to infinity. Because my radius was infinity, the center was irrelevant, and I will converge everywhere. So, a very nice problem, although not a very difficult problem. We didn't have to check endpoints because no endpoints existed. I do have a feeling that that will not be the case in our next example. In our second example of finding intervals of convergence, you might want to jump to conclusions. You notice that there is a quantity n plus 1, quantity n plus 2 on the bottom. And that might make you want to just jump up and say, oh, well, the radius is this or whatever. I will caution you, do not jump to conclusions. Let's actually do the work and see what happens here. The first thing we should do is take a look at this and realize that certainly our center is going to be at c equals 0. That's pretty easy to tell by looking at x to the n term. It's not a quantity or x plus c or anything like that. So our center is 0. The next thing we need to do is find our radius of convergence. And I'm going to do that the same way that we have been. We'll do the limit as n approaches infinity of the magnitude of the ratio. Now, because I'm looking at magnitude, this negative 1 to the n term will not be involved here. Rather, what I will end up with is x to the n plus 1 in the numerator. And in the denominator, if I plug in n plus 1 here, that will give me n plus 2. And if I plug in n plus 1 here, that will give me n plus 3. So there's going to be my next term. My current term, or rather the reciprocal of my current term, will be quantity n plus 1, quantity n plus 2. And then in the denominator, I'll simply have x to the nth power. Now, of course, because I'm trying to do convergence, I'll set that to be less than 1. If we do a little bit of cleanup here, let's see what's going to happen. As far as the x's, notice that I have one more x on the numerator than I do in the denominator. And so I'm going to end up with an x up here. Furthermore, I want you to notice that we do have an n plus 2 and an n plus 2, and those will cancel out, leaving me with just an n plus 1 in the numerator and just an n plus 3 in the denominator. Now, again, that is going to be less than 1. Well, as n approaches infinity, hopefully it's obvious for you to see that the n plus 1 term and the n plus 3 term are essentially going to cancel each other out. And so what I'm left with is that the absolute value of x is less than 1. What is that going to tell me? Well, that's going to tell me that my radius, r, is going to equal 1. All right, so far so good. It looks to me that what this means is that if my center is 0 and my radius is 1, then my interval is going to go from negative 1 to positive 1. The only problem is I'm not sure what kind of bounds to put on this. Is negative 1 included in the interval? Is 1 included in the interval? And so the way to test this is to actually let x equal these two values and see what happens to our original series. If I let x equal negative 1, then what we're going to get is the sum of negative 1 to the nth power multiplied by negative 1 to the nth power divided by this n plus 1, n plus 2 thing. Well, these negative 1 to the nth powers are going to cancel each other out. Whether n is positive or negative is pretty irrelevant here. The negative 1s are gone. And so what this is approximately equal to is going to be the sum of 1 over this bottom, which is n squared plus 3n plus 2. You can use any of the convergence tests that we learned back from 8.1 to 8.6, whichever one this falls in. You can compare this to a p-series test. And in fact, I would compare this to the p series 1 over n squared. Of course, this converges, and this series right here is always going to be less because the denominator is larger, and therefore this must converge as well. So my conclusion is that -1 does converge, and therefore should be a part of our interval. And there is my inclusive bracket. Let's try this one more time for x equals +1 and see how this works out. Don't make any assumptions. Just because one endpoint worked does not mean that both endpoints are going to work. So let's see what this looks like. It's going to be a very similar looking series, except that in the numerator, it won't always equal just +1. For this one, I will use the alternating series test. And I'm not going to show all the work. You can certainly work it out yourself. You've learned the alternate series test. You know how it works. And what we will find here is that this does converge by the alternating series test. So I can go ahead and put that there. So what I can conclude here is that our radius of convergence is in fact going to be -1 to +1. I certainly invite you to graph the function version of this series and then graph this series on top of it. And, I don't have the graph with me right now, but what you will find is that between -1 and +1, this series is a very, very good approximation for its original function, which is why our radius of convergence is -1 to +1, including both endpoints. Well, all that being said, let's take a look at one more example. Hopefully we'll get to see what it looks like when the endpoints diverge, just so you can, see what that looks like in practice. In our last example, you'll notice that we have all kinds of wacky stuff going on. We have an x-2 quantity. We have an n+1 quantity. Heck, we even have a constant this time. All kinds of stuff going on here. However, we're going to start the same. Take a look at this power series here and see if you can determine where the center is. Hopefully it shouldn't take you too long to determine that the center is actually at +2 here. So what I'm going to write, our center is at -2. Rather, I should say that is +2. +2. X-2, of course, to let that be 0, we'll have to put +2 in there. So there we go. There's our center. Now, in order to find our radius of convergence, guess what we're going to do? Of course, you already know we're going to do our ratio test. And I'm going to have to deal with all kinds of things here. To take our numerator to the next term, I need to substitute that n+1 in for n. And that's going to give us quantity x-2 to the n+2 power. In our denominator, instead of quantity n+1, I'll have quantity n+1 plus 1. Or I'll simplify that to n+2. That only makes sense. And then our constant, instead of 4 to the n+1, we'll have 4 to the n+2. So all kinds of stuff going on, like I said. Well, let's multiply that by the reciprocal of our current term. That is n+1 times 4 to the n+1. Don't let these n+1s bother you. They're just part of the series. Really nothing to worry about. Of course, on the denominator, we're going to have x-2 to the n+1 power. And we want that to be less than 1 for convergence sake. So, once again, let's go ahead and simplify, do a little cleanup here. And what we'll find is these quantity x-2's, well, we have one more of those on top than we have on bottom. So there is my quantity x-2 that I'm left with. n+1 is not going to cancel with anything, so I'll keep my n+1. And as far as my 4 goes, I have n+1 of these 4s on top, but I do have n+2 of them on the bottom. So I'll leave my 4 on the bottom here. I have my n+2 that didn't cancel with anything. And then my x-2, I already dealt with that. So here's what I get after simplification. My limit as n approaches infinity, hopefully you can see that these two terms right here are essentially going to cancel each other out as I approach infinity. And what I'm left with is the magnitude of x-2 over 4 is less than 1. One last thing I got to do, multiply both sides by 4, and what I'll have is x minus 2. Absolute value, of course, is less than 4. So what do I end up with as my radius? Well, I just found my radius, and it is r equals 4. Of course, now that I have my center, now that I have my radius, I can go ahead and set up my interval. 2 minus 4 would give me -2, and 2 plus 4 would give me 6. These will be the endpoints of our interval of convergence. So, just like in our last example, let's see what happens when I let x equal -2. Let's see how this affects our original power series. What we're going to end up with here is the sum of, well, when I plug -2 in for x, I'm going to end up with -4 to the n plus 1 power. In the numerator, I have n plus 1 and +4 to the n plus 1. What is this going to do? Well, the 4's are essentially going to cancel, and what I'm going to be left with is an alternating series. I have -1 to the n plus 1 power. Don't be worried by that n plus 1. It's just an alternating series, and I have n plus 1 on the bottom. So what's going to happen here? What kind of series does this look like? I did say it was an alternating series, so I kind of gave that away already. But is this going to converge or diverge? Again, go back to our alternating series test. You will notice two things about this alternating series. You'll notice that the limit as n approaches infinity is certainly 0. That's our first condition. And you will notice, if you try, that each next term is smaller in magnitude than our current term. Those are the two conditions I need to satisfy in order to say that this series, this alternating series, does in fact converge. And therefore I can say that -2 converges. Well, what happens when x equals 6? This is where we're going to have a little bit of excitement. I will have the sum of 4 to the n plus 1 power. This is +4 this time. In the numerator, I'll have n plus 1 times 4 to the n plus 1 power. I think it's fairly easy to see that the 4 to the n plus 1 powers are going to cancel out, leaving me with 1 over n plus 1. That's a series that we have seen many times before. You can consider it very similar to the p series with p equals 1. And of course, what happens to a p series with p equals 1? It diverges. And so I end up with a radius of convergence, and I'll write it down here. Radius of convergence in this case will be -2 to 6, and this will include the -2, but not the 6. The -2 will converge, the 6 will not, as we saw here. So, in this lesson, we've explored centers of convergence, we've explored radius of convergence, and we've put those two concepts together in order to find the interval of convergence. Remember, the interval of convergence is simply telling us in what neighborhood the power series approximates its original function. We've had to explore both of those. We've had to look at the endpoints, and it's a lot of stuff, but you see that it follows a very predetermined script. So it's not extremely difficult. It's just sometimes a lot of work. So with all that in mind, good luck as you explore your 8.8 assignment.